This is part 2 of chapter 18. We still have left to cover the X-bar and R chart, which uses measurement data, something you can find an average for, as well as process capability. There's a lot of other reading material, but you're kind of responsible for reading that on your own. Anyway, when you have measurement data, and in the textbook, page 18-18, there is they use a file called Hotel2, and they compute both limits for an X bar and an R chart, and I've got them here. The problem, well, it's no problem with it, but the reason that you need two charts for one set of data is that you have not only, when you compute averages, you have the average, the mean, and you also have a dispersion or a spread that data takes on. So the R chart is used to look at whether the spread is within the limits that you compute, that you would expect from your process, and the X bar chart is used to look at whether the mean is where you think it should be. So back with Excel, our file is called Hotel 2, and for this file, now I can't remember. I am thinking, let me look. Okay, I guess that's going to be all right. Okay, so we're going to try it this way. It may not work. I can't remember whether I have to actually manually compute the X bar and the R in order to make this work, or whether it does it from the data looking at the range. Since I can't remember, I really don't remember. For this one, I do know that you would not select the first row with the titles in it. So as you can see, for this data, Hotel 2, I think these are delivery times for bags, 28 days worth of data, and they have taken samples of 5. So all the data's here, and they've measured the time I think that it took for the bags to be delivered to the hotel room. Anyway, so this is our data. PHStat again makes things really easy. I go to control charts, X bar and R, and my subgroup size is 5. I don't think it's going to work this way. I think I've messed up. But I'll try to select it and see if it will do that. Uncheck this box, and then I want X bar and R. So I go back and I'm going to select just the data, not the observation, the day number, and not the title, and take out these 2 check boxes. And I think I can say okay, but it may or may not work. No, that's no. What it's done is it's calculated it for everyone. So this is, I messed up. So let me just go back, and I'm going to delete all of these sheets. Sorry, I've forgotten how I did this. Delete, 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 and delete, delete. Yeah, I do want to delete it. Okay, so let me tell you what you've got to do. So the first thing you've got to do is you have got to actually compute the X bar, which is just the average for each of the time periods you've selected. So your X bar, I'm going to compute it right in this column, and I'm going to go ahead and I'm going to make these bold. I'm going to right justify them, and I'm going to underline them so they'll kind of match the rest of the data. Anyway, for my X bar, what is just an average equals average of this range of 5 cells. And then I'm going to press enter, and I'm going to copy this down over the 28 days, and this should be my average for my data. The range is a little more complicated. So for my range, or my R, we're just going to call it R, what we're doing is we're looking at each one of these rows in our data, and we are subtracting off the smallest time from the largest time. So in this first one, it would be 11.7 minus 6.7. But I don't want to go through 28 days worth and do this. So the method I found that works is I put in two functions. So equals max, and I select the 5, and it's going to identify the biggest number, and in my parentheses, minus min. So min does the same thing. So just select the same 5 data pieces of data. So let's just say B2 to F2 for each one of them, and press enter, and that tells me my range. So it will compute a range all the way down. And the reason, by the way, that you see this little caution box is that it's detected that there is another column over here at A that has number in it, and it's confused. It wants to know if you want to go back and include that, but we don't. So now I've got my data in a format that I can use in PHStat. Go back to PHStat and control charts, XBAR R. My sample size is 5. For my range, I'm going to pick off these ranges. Again, I'm not going to select, I have in my notes, do not select this. I'm not going to select the title. And then I'm going to click on XBAR and R. Again, I'm going to go back and I'm going to select just the XBARs for those 28 days and unselect that box. And then I'm going to say OK, and it should create my charts. So as you can see, and you remember from last week, it does the calculations. So it actually figures my XBAR, my R. It's even got control chart factors table over here with the numbers they used. If you read through the book, you'll see that. And it's got the columns if you had to do it in Excel. The first thing you look at with your XBAR R chart is your R chart. At least that's the way I've always been taught, to look at that first. So if the range is not in, then you stop. And you don't even look at your XBAR chart, because if your range is not inside the upper and lower control limits, it means that you have assignable cause variability and something has to be fixed. So you can see very clearly our lower control limit is 0. Our upper control limit's up here somewhere. I don't know what the number was, but you can see the dotted lines. Our center line is the R bar here in the middle. And, you know, here's all my observations, and they're all well within the upper and the lower control limit. So my conclusion at this point would be no problem with the R chart, but I do have to look at the XBAR chart. So click on the other tab. There's my XBAR chart. And you'll notice it's set up the same way. Has a center line, little red line. It has the upper and the lower control limits, and then the blue is where it's plotted out each one of my 28 observations. And they're well within the limits also. So my conclusion at this point is there's no problem with, you know, my control chart calculations. So I would go ahead and use this data. In your calculations, and I'm pointing this out because you're going to run into this sooner or later. On your calculations for they don't have it on here. Okay, so you have to look that up in the table. It's not here. I thought it might be. Okay, it's not here. But there are different ways to do the rest of this, which is the process capability part. Again, let's go back to the notes, my R chart, XBAR, and by the way, this phase 1, phase 2, sometimes it's called runs rules. We talked about phase 1 earlier. This is the part where we've done with all these control charts we've looked at. We just want to assess whether our process is in control or out of control. So they identify this assignable cause variability. Phase 2, after we've determined our process is in control, then you start gathering data from this process over time, and you monitor it, and you make adjustments when you need to. Now, you don't want to, if you remember from your reading about the red bead, you do not want to adjust your process every time it gets a little bit away from the center line, but you do want to look for patterns in your data. So these are some common ones. Some of these came from different people. Western Electric Handbook, again, the one I said is very important, you know, has a whole list of different things. I took these from Montgomery's book, which is a well-known one, but he took them right from there. And here's some others, you know, so, you know, there are all kinds of rules and things that you look at and should look at if you're using it over time. Process capability is used when, usually it's used because you're in a situation where, excuse me, management has set a set of specifications for producing the product. It may come from engineering probably, and they have specifications. So you're making bags of potato chips, and they say that the bags of potato chips should weigh between, if it's the midline is 10 ounces, that's what they want. They're willing to accept 9.9 ounces up to 10.1 ounces. That's their specifications. That is not necessarily what your process is capable of doing. And if they want something that is not what your process is capable of doing, this is a good way to kind of show people that, you know, you just can't do this using the process you have. If they want something you're not capable of doing, then you're going to have to make some big changes, usually buy new machinery. It's not just an adjustment, it's a purchase new machinery usually. Retrain people, get better materials, but something's got to make a big change. For some of these process capability problems, you would be given a value for a standard deviation from the process, computed just like we did earlier this semester. If the standard deviation is not given, you would compute it by taking your R bar and dividing it by a D2 value, which you would find in the tables, which are at the back of your book, the control chart tables. The D2 wasn't on the one from Excel. I was kind of disappointed in that, but that's, you just have to actually look up. It's a little d, lowercase d, D2. So for process capability, there are basically two things you're looking at. First thing you're looking at is something called a process capability ratio, or CP. And basically what this looks at is whether the variation that is inherent in your process is within the tolerances, these come from the spec limits, that is expected from the process. So where you see the USL and the LSL, this is the upper spec limit minus the lower spec limit. And what it does is it takes the limits that management wants and divides it by the range that you would expect to find in your process. So this average R divided by D2 is used in lieu of a standard deviation. And since 6 standard deviations account for about, what, 97 or 99.7% of the observations, you're looking at the range. So the range from that they want divided by the range your process is doing. If you're, think about it for a second, if your process capability ratio, CP, is less than 1, that means that your process range is greater than your tolerance range, and your process isn't capable of meeting the specs. So again, you'd go to management and you'd say, look, this is what my process can do. I can adjust it all day long, but I'm still going to have a big pile of bad things over here because it's not capable of doing this, what you want from it. If your CP is greater than or equal to 1, then your process range is less than your tolerance range, and your process is capable of meeting specs. So the example that they've got here in the book, and I just basically have this typed out, you have to kind of do this by hand, page 26 in the chapter, example 18.2, they have spec limits of 12 ounces plus or minus 0.18 ounces. I don't remember what this was for. But when they did their X-bar R chart, they had a sample size of 4. The X-bar, the average across those 4 samples was 12.02. X double bar, this is the average of the averages. And your average range ended up being 0.1 ounce. The D2 value, got that again from the table for a sample size of 4. You just read across till you see the little D2. It's in the back of your book. And then the spec limits, I computed those using the 12 plus or minus 0.18. So 12 minus 0.18 is 11. No, 12. Yeah, 12 minus 0.18 is 11. I don't know. I've got 8 there. 11 point. It should be 8.2, I think. And we'll put the 2 out there. 8.2. And the upper spec limit is 12.18. So you just subtract it off from 12 and add it on to 12. So I put my numbers in. I've got my 12.18 minus 11.8 in the numerator. The denominator, I've got 6 times my average range of 10.10 divided by 2.059. That's my D2 value. And I came out with a measurement of 1.24. Since my process capability sorry, my process capability ratio is greater than 1. That tells me that my process range is less than my tolerance range, and I have no excuse when management comes to me and says, you know, this is what we want your process to do. So anyway, that's when you look at it, process capability. The other thing that we're going to do is something called, I'm going to skip this part, because I really don't think that does us any good. I'm going to look at the Process Capability Index. You can read back through the other if you have any desire to, but I really don't care about that so much as I do the Process Capability Index. Anyway, this is index number that you compute that helps you determine whether your process mean is centered at the specification mean or whether it's shifted up or down so far that it's going to cost you to be producing bad items. So you could have the range that's okay with your process capability ratio, but you could have an index that says you got a problem with where the mean is at. So this is example 18.3 on page 18-26, and the formula looks terrible. I apologize, nothing to be frightened about. CPK is Process Capability Index, and it says equals min. This is not linear programming. This is nothing scary. You're not doing anything with this. You're just saying pick the smallest of these two computations you're going to do within this big bracket. So on the lower side, you're going to take your process mean and subtract off your lower spec limit, divide it by 3 of these standard deviations. So your average range divided by D2 times 3. And then on the upper side, you take your upper spec limit and subtract off your X double bar and divide it by 3 standard deviations again. So it says min 1.37 and 1.10, and min means pick the smallest number. So the smallest number is 1.10. So what this tells me is if the process capability index is greater than 1, it means my process is capable. Nothing has shifted so much that I should be having a problem. So that's what this says. If it's less than 1, that means that your process mean is shifted closer, so close to one of these 2 spec limits, either the upper or the lower, it's going to produce defects. And if it's exactly equal to 1, that means your process mean is exactly centered on the spec mean. So anyway, this one's capable, no problem. You've got a little shift, but it's not enough of a shift to cause a problem. Anyway, that's the calculations in chapter 18. You will, of course, want to read section 18.7 and 18.8 carefully, where they talk about total quality management and W. Edwards Deming, and then the Six Sigma, which is very important. And by the way, once you finish this class, you're still enrolled in classes next semester. The School of Business and the College of Engineering together sponsor, along with Boeing, a series of 3 classes that train you in a green belt in Six Sigma, and it's free of charge for you. You have to be on campus for 1.5 Saturdays, 1 Saturday to go through the training, and the next Saturday half a day to take the test. And I think it's open book, open note. Anyway, and for that you get to put on your resume that you have a green belt in Six Sigma, which is a wonderful thing. Our students take advantage of that a lot. Thank you.